We come now to the lowest level of digital systems, and that is the humble FET, Field Effect Transistor. To make digital circuits, all we need are FETs, nothing else. The internals of FPGAs, CPUs, etc. are made up of millions or even trillions of FETs. Given a FET, we can make logic gates. Given logic gates, we can make flip-flops, although technically there's a slightly better way of making flip-flops, but it also involves using FETs. With FETs, we can build everything we need to build digital systems. By understanding FETs, we will understand the physical causes of contamination delay and propagation delay, and will understand why digital systems are robust to noise. The internals of a FET look something like the following. It's made out of silicon, and you dope different regions. So this is a P region, this is an N+ region. So it's doped to have some free holes here and some free electrons here. There are 4 pins, although often you only see 3 pins. That's because often the source and body are connected together inside the case, so that effectively becomes 1 pin, and you've got the gate and you've got the drain. Perhaps the easiest way of understanding how a FET works is that the voltage between the gate and the body, also known as the substrate, the voltage between the gate and the body determines the resistance between the source and the drain. So it's a voltage-controlled resistor. In terms of a water analogy, imagine a piece of pipe connecting the source and the drain. So a short segment of a rubber tube, like a garden hose. The gate to body voltage determines how tightly we are squeezing in the middle of this piece of pipe. If we squeeze the pipe, then no water can get through. If we don't clamp at all, then we can have the maximum flow of water between the source and the drain. So by squeezing closed on the pipe, we can limit the amount of water that can flow through from the source to the drain. The distance from here to here is referred to as the channel length. So actual electrons need to travel from the source to the drain, and they have to travel a distance of L. That's the length of the channel. The width of the channel goes into the page, and that determines what the lowest resistance can be. It's like a pipe. The wider the pipe, the more water you can fit through. Well, the wider the channel, the more electrons you can fit through. So the length determines how far the electrons have to travel, and that's related to how fast a FET can react. As computers get faster and faster, the FETs inside them are getting shorter and shorter lengths between here and here, so that as soon as the gate to body opens up, allowing electrons to flow, they have a very short distance to flow. The computer can compute faster by having a smaller length for the channel here. To summarize, the gate to substrate voltage, and since the substrate's normally connected to the source, we normally say the gate to source voltage, although technically it's the gate to substrate voltage. The gate to substrate voltage determines the resistance between the source and the drain. Just think of the gate to substrate as a clamp on a piece of pipe. It can clamp down on the pipe to limit the flow of electrons, or it can open up and allow as many electrons as possible to flow through the channel here. As with any electrical device, it helps to separate out the DC properties or steady state properties from the AC properties. So in DC, if we apply a voltage to the gate and just leave it there at a constant voltage, this oxide layer does not conduct. And that's one great thing about a FET. Compared with other transistors where the base current does draw current, for a FET, the gate current is negligible. There's essentially no gate current at all in steady state. There is a switching current because this forms a capacitor, but in steady state, a FET does not draw any current into its gate, which is one of the attractive features for using FETs rather than other transistors. Anyway, for DC voltages, a constant voltage at the gate, no current will flow because this does not conduct, this oxide region here, but it looks like, and it is, a capacitor. So as we change the gate voltage, we're charging up or discharging this capacitor here. And we won't go into the solid state physics, but basically by changing the charge stored in this capacitor, we influence how easily it is or how hard it is for electrons to flow through the channel. A bit later, when we come to understanding where delays come from, it's because the gate to body forms a capacitor and the source to drain forms a resistor. For this course, it's essentially enough to know that with a FET, the input looks like a capacitor and the channel looks like a resistor. So if this is the source, so we're using an N-channel FET here. Later we'll learn about a P-channel FET, which is essentially just replacing electrons with holes as the mobility carrier. Anyway, with an N-channel FET, the gate to source is going to look like a capacitor and the source to drain is going to look like a resistor. If we know that, and if we understand what happens if I put a voltage here and put a resistor here and connect this to ground as well and have a look at the output here. If we understand as I vary the voltage here going into my FET, this is a FET, not a capacitor, and this is a resistor. If I understand what the output voltage looks like, so if I've got V in here and V out here, if I understand what this graph looks like in steady state, then I'm well on my way to understanding how FETs work for this course. We will simulate this circuit presently in LT Spice to see exactly what we get, but we should start off with some guesses first. So imagine first that V in is 0. So we're looking at this point here. V in is 0. That means there is no voltage from the gate to the source. That means, as we'll see presently, that the channel is off. Nothing flows through the channel except for some very small leakage current. If that's the case, that means all the current flows through this resistor here. Nothing goes through the FET. So if we have a 5 volt supply rail here, that means we expect the output is going to be 5 volts if the input is 0 volts. At the other extreme, let's assume that if I make the input 5 volts, that the channel becomes wide open. So as many electrons as possible are going to flow through the FET, limited only by the width of the FET. So the resistance from the source to the drain is going to be very small. How small? It depends on the width of the channel. If we buy a single FET from the electronics shop, it's probably going to have a very wide channel. We can't fit such wide channels into digital systems if we want to use millions or trillions of FETs. So in a digital system, there is going to be some channel resistance that's significant. Anyway, depending on the value of the resistor here, we basically have a voltage divider. We've got our R up the top from here, and we've got our variable resistor representing the source to drain resistance. And that means that our output is just a voltage divider. So if we call this resistance RC for channel, and that depends on the input voltage, then V out is going to be equal to RC on R plus RC times the input, the supply voltage, 5 volts. So as we change RC, we're going to get a different voltage coming out, and we change RC, we change the channel resistance by changing the voltage from gate to source. When RC is very small compared with R, the output's going to be approximately 0. So depending on this value of R, we expect that when the input is 5 volts and the channel is wide open, that the output is going to be very close to 0 volts. So we've got 2 points here, one here, one here. If we're somewhere in the middle, then the channel is going to be partially open. RC is not going to be 0, which would correspond to here. RC is not going to be infinite, which will correspond to here in the ideal case, 0 and infinity. It's going to be somewhere in the middle. And depending on what it is relative to R, will tell us what the voltage is around here. Now at this stage, we can't say much more. We don't know. Is it going to be a straight line like this? Is it going to be a curved line like this? A curved line like this? And an S line? We don't quite know yet. Since it's not too important, we're not going to try to work out the answer by looking at the solid state physics. Instead, we're now just going to run some simulations to work out exactly what this curve is going to look like for different values of R. And that, together with the fact that the input looks like a capacitor and the output looks like a resistor, these two facts are basically going to be enough for this course. After running LT-Spice, it should look like this. Download the accompanying zip file, then File, Open, go to wherever you downloaded the zip file and have unzipped it, and we'll start off with the FET directory, and we open the fet.asc file. This gives us here a voltage source going into an N-channel MOSFET. We have a pull-up resistor, and we have our supply rail here. The output is taken at the drain of the NMOS. Our supply rail is at 3.3 volts. Our resistance R is going to change. We're going to do 4 simulations. R is going to be 1K, then 10K, then 100K, and 1 megohm in the 4 different simulations. The input voltage V1 is going to range from 0 volts to 3.3 volts in increments of 0.01 volt, and it's a DC analysis. That means that the input is going to be set to first 0 volts, you wait for everything to stabilize, then you find out what the output is. Then V1 changes to 0.01 volts, wait for everything to stabilize, then read off the output. In this way, we can get a graph of the V in versus V out. To create this N-channel MOSFET, we needed to use a library file. Cedra and Smith wrote a classic book called Microelectronic Circuits. An accompanying file to that book is this short LT-Spice library file. If we open it up, File, Open, in the same directory as we were before, but we need to list all files. We see that it's right here. Double click it, and it defines a few things. We don't need the BJT. If we scroll down, we don't need the diode. We don't need the other BJTs. Here we have our P-channel MOSFET and our N-channel MOSFET. If we read it, we see it's a basic model for the NMOS 5 micrometer CMOS technology. So this is dinosaur technology 20-30 years ago, but it's good enough for our purposes. It defines an NMOS model for a particular NMOS FET, and these are the parameters in here for it. If you want to understand how to model FETs and how SPICE works in general, then there are books that dive into that for you. All we need to know is that this is a fairly typical NMOS FET that you at least used to find in CMOS technologies. 5 micrometers is considered quite large by today's standards. Nevertheless, the fundamentals never change, and it's more than good enough for what we want to do. If we go back here, we want to run this circuit to see what the output looks like as we vary the input. So we just click on the running man here and close this to give us more space. If we jump up here to window, tile, which is better, maybe vertically. And we don't have anything here because we need to attach our oscilloscope, so to speak. All we need to do is move our mouse over the point where we want to get a voltage readout and left click, and we get 4 beautiful traces here. How do we interpret this? Well, because we asked for a DC sweep, the horizontal axis down here is simply going to be the input voltage. So when the input voltage is 0, we go up here and we see that the output is going to be 3.3 volts. And when the input voltage is 3.3 volts, we see that the output for some resistance values is basically 0, but for others it's well away from 0. So the reason we have 4 traces here is because we're also doing it for 4 different values of the pull-up resistor. So one of these lines corresponds to 1K, another to 10K, another to 100K, and the other to 1 megohm. Unless you figure out a way of putting a legend onto this, it might be a bit hard to work out which is which, but we can solve it by using our understanding of how this FET is going to work. When the input here is 3.3 volts, then the channel is going to be wide open, allowing as much current to flow as possible. This means that the resistance here is going to be very small. I'm not sure exactly what it is, might be 1 ohm, might be 20 ohms, but it's small. If this resistance value here, R, is also very small, then, so for example, if this were 20 ohms and this were 20 ohms, then we'd have a divider here where the output would be half the input voltage. And so you see when R is small, we expect something like this green curve here. So this green curve must correspond to 1K. And in fact, if at 1K we have the output being about a half, that actually suggests that the resistance here is about 1K when this FET is supposedly wide open. If this resistor were much larger, then even if this were 1K, the output's going to be very close to 0, and we see that here. So R equals 1K, R equals 10K, the blue one, R equals 100K, the red one, and R equals 1 megohm, the cyan one. When the pull-up resistor R is large, we get this very beautiful rapid transition here. This is exactly what we want in digital logic. This actually represents an inverter. When the input is 0, the output is 1, a logic 1, high. When the input is a logic high, the output is a logic low. And the sharper the transition, the better. And we get this with a high pull-up resistor here, a very sharp transition. This makes digital logic immune to noise, which we'll discuss in a later lecture. There are a number of disadvantages of using a pull-up resistor that we'll cover. Here we see that the transition occurs not halfway, but closer to the low side, just under 0.9 volts, as opposed to the high of 3.3. So this does implement an inverter, but it's not desirable. We will later replace this with a P-channel FET and get exactly what we need. But for this video, we're just going to continue with a pull-up resistor here to demonstrate the basic principle. When we use an N-channel FET in LT-Spice, we need to specify the length and width of the channel. And here we've chosen the length to be 0.5 micrometers and the width to be 1.25 micrometers. That I simply took from the book by Cedra and Smith to be typical of the technology that was used back when the book was written. In terms of understanding the steady-state behavior of an N-channel FET, this is all we need to know. If we understand the behavior of this circuit, then we understand the DC characteristics of a FET that we need for digital systems. What we now want to quickly look at, though, is how the FET behaves when the input changes. And we're going to see that the input looks like a capacitor and the output looks like a resistor. To try to demonstrate this, we're going to build some test circuits to see what goes on. To explore what the input to this FET looks like, we're going to make some changes to this circuit. First, select the Cut tool and get rid of the sweep parameter. Press Escape, right click this resistor, change its value to 1K. We need to insert a resistor here. Currently this voltage source forces the gate voltage to change immediately. By putting a resistor here, we can see whether or not the gate voltage will actually change immediately or not. So cut tool again, break it here, go up, select resistor. It's round the wrong way, so choose rotate, come back down, add it here, press escape, choose the wire tool, wire it up here, press escape, go up to the zoom to fit again, and we don't want a DC analysis, we want an AC analysis. So right click this one here, click advanced, we want a pulse, we start off at 0 volts, we're going to rise up to 3.3 volts with no delay. We want a square wave, so we need a very fast rise time. We can't have a 0 rise time, that's unrealistic and will cause the simulator some problems. So we've got a rise and fall time of 0.1 nanosecond. We're going to be on for 20 nanoseconds and off for 20 nanoseconds, having therefore the period is 40 nanoseconds. Press OK. And we don't want a DC analysis, so right click this statement here, and we want a transient analysis, and we're going to stop after 80 nanoseconds. Hit OK. We need to give a value to this resistor here, so right click, oops, wrong one, right click the resistor and choose its resistance to be 1 megohm. Then click the running man, and here's the input, it's a nice square wave. Here's the gate of our FET, and we see that we get a curve that looks the same as if we were charging up a capacitor. So this graph justifies that the input to a FET looks like a capacitor. Now in principle, from the time constant here, we could work out what the capacitance was, but I don't quite trust the different parameters we've used here, so we may not get a realistic value. The key point though is the input to a FET looks like a capacitor. The relevance of this is that if we connect two logic gates together, then the output of one logic gate might change from low to high, but it takes time for the input to the next logic gate to register that, because the first gate has to charge up the gate to source junctions of the FETs in the second logic gate. So basically this is the reason why we have got propagation delays and contamination delays. The FET does not immediately react to a change in the input, it slowly charges up. So there's a contamination delay when the FET hasn't really seen the input change, and then there's a propagation delay when the input to the FET has finally reached the value at the output of the previous gate. To try to justify what we just said, let's now go back to our original circuit, and we're going to add a capacitor to the output here to see what we get. So if we were to connect this to a logic gate, we believe the input to a logic gate looks like a capacitor, so let's just add a capacitor here and to see whether or not this behaves like a resistor. If this behaves like a resistor, then when we connect this to a capacitor, we should get a charging curve as before. We need to make a number of changes. Let's start by changing this back to a pulse again to get our square wave. That's done. Before we forget, change our analysis to be a transient analysis for 80 nanoseconds. We are going to add a capacitor here. This simulates the input to the next logic gate. We need to connect it to ground, and we need to give it a value. We'll start off with a 1 picofarad capacitance here. Having a resistor here is not so realistic. Nevertheless,
let's make it a 10K. Later in the course, we'll replace this with a p-channel FET and look at connecting two such logic gates together to verify that everything works. But initially, let's just do the simpler experiment. For clarity, we don't need the step statement anymore either. We press the run button and we have a nice input here, and we see that yes, we have these charging curves as we expect. So maybe it's not conclusive proof, but later we really can build a circuit with a p-channel FET here, n-channel FET here to model an inverter. We can connect two inverters together and we will see that we do have this charging discharging response, which causes contamination delay and propagation delay that we saw earlier in the course.